Okay, folks, let's jump right in here. Remember, I said the first thing we're going to do is we're going to talk about, let's see, let's add in the Excel solver here. So if you click on, let me just go back here, make sure I show you on, click on File, go all the way down to Options, and you'll get this, this big list of Excel mumbo jumbo. Go down to Add-ins. Click on add-ins, and then let's see, manage Excel add-ins. Just click the drop down. Let's actually just go to Excel add-ins. If you hit go, and then you'll get this this option here to add in a bunch of analytical goodies. The one that you want to, we'll certainly use the analysis tool pack down the road. So go ahead and add that in, and then also click on the solver add-in, and you'll be good to go. And I'll show you how to get to that in just a minute. So once you have that, you'll be ready to go. So what I want to do here is I picked out two problems. Some of the problems you'll note in the homework are have a little tag after them that says algorithmic, which means that those problems are going to have some different values for all of us. However, the approach will be exactly the same. So I picked out one that is common to everybody. That's 7.41, and then 8.29, which is algorithmic. So we definitely want to read these problems here because we're going to model these. So let me start with, and I apologize for reading to you, but I want to certainly highlight some things as we go forward here. So I'll pick up over here on the top right. Southern Oil Company produces two grades of gasoline, regular and premium. The profit contributions are 30 cents per gallon for regular gasoline and 50 cents per gallon for premium gasoline. Each gallon of regular gasoline contains 3/10 of a gallon of grade A crude oil, and each gallon of premium gasoline contains 6/10 of a gallon of grade A crude oil. For the next production period, Southern has 18,000 gallons of grade A crude oil available. The refinery used to produce the gasolines has a production capacity of 50,000 gallons for the next production period. Southern Oil's distributors have indicated that the demand for the premium gasoline for the next production period will be at most 20,000 gallons. Formulate a linear programming model that can be used to determine the number of gallons of regular gasoline and the number of gallons of premium gasoline that should be produced in order to maximize total profit contribution. If required, round to do, that's fine. So first of all, let me just go back to what I said in the overview about linear programming and linear optimization problem. If as you read through this again on your own, you're going to note that the relationships between the variables are very well known, and we notice that there are some constraining situations here that we will be able to model. So the first thing, remember I said, the first thing we're going to do is we're going to define decision variables. And here they are down here, and I think this is actually done for you in the homework. So R is going to be the number of gallons of regular gasoline produced, and P will be the number of gallons of premium gasoline that are produced. So in translating the written into Excel, and I'll talk about the strategy here in just a moment. But the first thing I'll do is just put a little tag here and say the decision variables, number of gallons of regular, number of gallons of premium, or you could just put R or P if you want to do that. Those values will go right here, right? Because these are the values here this is actually what we would consider to be the optimal solution once the model is solved. And they will contribute to the objective function and the constraints as we go through the problem. Remember, we said that the profit contributions for each type is 30 cents per regular and then 50 cents per premium. Remember, let's see, back from the reading, it says formulate a linear programming model that can be used to determine the number of gallons of regular gasoline, the number of gallons of premium gasoline that should be produced in order to maximize total profit. So what we're going to do here is we're going to have an objective function that we want to maximize, and the objective function is based on the number of gallons of regular gasoline that will be produced and the number of gallons of premium gasoline that will be produced. And remember that the profit contributions, 30% per regular gallon, 50% per premium gallon. So the objective function here, and I've already put a formula here, and I'm going to share this sheet with you. So I just don't try to write this all down. I'll share the sheet with you, and you can have this if you want to use it to get started with your homework. What this does is there's a function in Excel called sum product, which effectively takes the product of, in this case, the number of gallons of regular, number of gallons of premium, which is in cells D3 and E3 as an array, and it multiplies it respectively times the profit. So this sum product of D3, E3, and D4, E4 is effectively this value times this value plus this value times this value. Now you could type that into Excel that way if you wanted to, but I think you're going to find this sum product option is probably going to be valuable to you as you go through these problems. All right, so, and again, I will provide the sheet to you so you can look at this and make sure you understand the syntax. So we've defined the decision variables and we have defined the objective function. Now, here's where the constraints come in. In the way I have done this, this ST that you'll see in the book, so we're going to use these decision variables to optimize this condition, and the ST means subject to these constraints. And so if you go back through the reading, you're going to notice that the problem is constrained in 5 very discrete ways, right? Remember that we have a maximum of, 18,000, for the next product, Southern has 18,000 of grade A crude available. The capacity for refining is 50,000 gallons. The maximum amount of premium that is available during the next production cycle is 20,000 gallons. And then we have what's called a non-negativity constraint. If you remember back what I talked about in the problem that we solved graphically, the reason that we really only looked at the first quadrant of the XY plane is because both of the variables have to be greater than or equal to 0. So there's a non-negativity constraint that goes along with each variable. So let's talk a little bit more about these constraints. Let's see. Southern Oil has Southern Oil produces 2 grades of gasoline, regular and premium. The profit contributions are 30 cents per gallon for the regular gasoline and 50 cents per gallon for premium gasoline. Each gallon of regular gasoline contains 0.3 of a gallon of grade A crude oil, and each gallon of premium gasoline contains 0.6 of a gallon of grade A crude oil. Now, since we only have 18,000 gallons of crude oil available, we have to constrain the problem in that manner. So the total number of gallons of grade A crude oil that we will use will be 0.3 times the total number of gallons of regular fuel that we produce plus 0.6 times the total number of gallons or total number of gallons of premium fuel that is going to be produced. What I have done in this value or in this column, I have actually computed that value. And this time I did not use sum product. I should have, but that's okay because I used it exclusively on 829. But this might be more helpful to show what exactly the sum product formula would be doing. I have D8 times D3 plus E8 times E3, and that will compute the total number of gallons of grade A crude oil that I'm going to use. And I know that that has to be less than or equal to 18,000 based on the availability of grade A crude. Let's see. Then it says Southern has a refining capacity of 50,000 gallons. So effectively here, what I've said regarding the coefficients, when I take 1 times what is effectively R and then 1 times P, what this effectively comes out for, or comes out to mathematically, is just D3 plus E3, or R plus P, the total number of regular gallons and the total number of premium gallons must be less than or equal to 50,000. The next constraint, I only have, let's see, 20,000 gallons of premium fuel. So again, if the coefficient of the R variable is zero, and the coefficient of the P variable is 1, this effectively becomes P is less than or equal to 20,000, right? That will give us this constraint. And then finally, we have the non-negativity constraints. This would be R is greater than or equal to 0. And the next one is P is greater than or equal to 0. So what we have done to this point is we have defined the decision variables, we have set up the objective function, and we have algebraically defined the constraints. The next step here is to put all of this information into Solver. So if I go to the Data tab at the top and I go over here to Solver, I have actually already done this for you. So the first thing that you are asked to do here is to find the objective function. So all you have to do here, let me just delete that and show you. So all I need to do is click on cell E5, and that knows, or that way Excel knows to optimize that condition. Then the decision variables, it says what can Solver adjust to satisfy these constraints while also making the objective function as large as possible. So the two decision variables, I have them in green right here. So as long as the cursor's in this cell, all I have to do is highlight the first one, pull it over to the second, and then I have identified the two decision variables. The next thing is the constraints. Let me actually delete these and re-add them because this is pretty cool. We're going to do this all at once effectively. Now, what we need to compare in Solver are the computed cells for each constraint and what is really what's called the right-hand side variable, or what's the maximum number of, actually, let me call this, no, let me leave this just that way for now. We'll, let me go back to Solver here, Data, in Solver. We're still in good shape here. So for now, we'll say that the right-hand side represents the maximum. The book may have done that slightly different, but I don't want to confuse that at this point. So here's what we're going to do. Let me go back and make sure I don't confuse Solver. So the objective function is still in E5. The decision variables are D3 and E3. So what I have to do now is put the constraints in Solver. Notice that the first three all are of the form less than or equal to. So I can do all three of these at one time. So these cells must be less than or equal to the corresponding values in the right-hand side. And if I just hit OK, that effectively adds all three of these constraints. And since these two are greater than or equal to, I can add those at the same time. So I will just click on these values, just change the direction of the inequality, and then click the right-hand side values and hit OK, and we are done. The last thing that we need to do here is just simply hit solve, and the model will be solved for you. And so what do we find here? The optimal solution is not the value of the objective function. The optimal solution is the mix of decision variables, right? So this is effectively the point in the feasible region that maximizes this objective function while also satisfying all 5 of these constraints. So you can go through that and you can convince yourself that the optimal solution does in fact satisfy all the constraints, and that would be a probably not a bad thing for you all to do here for this first run. So I'm gonna stop here. I'm actually gonna put together another video for section or for problem 8.29. But again, I will post this file along with the video, and if there are any questions, please let me know. Hope this is helpful. Thanks.